cylinder and the piston must be of perfectly insulating because there should not be any exchange of heat between the system and surrounding. There is no change in temperature of the system and hence it is isothermal process. According to the substitution procedure, we have to substitute the upper limit in the variable inside the bracket minus the lower limit. In isothermal process, temperature remains constant, whereas in adiabatic process, the heat energy remains constant. Is the basic difference, as we all know. Hello everyone, welcome to session 3 of chapter 12 Thermodynamics. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Till previous session, we have studied about the basic of thermodynamics, different processes in thermodynamics, that is isothermal process, adiabatic, isobaric, isochoric and many more. In today's session, we are going to learn more about the remaining process. Let us begin with the expression for work done in an adiabatic process. In the previous session, we have derived an expression for work done in an isothermal process. So, we have to move on now to study about the work done in adiabatic process. So, to derive this expression, let us consider 1 mole of ideal gas which is contained in a cylinder with perfectly insulated walls and piston. Because we know the condition for adiabatic process, the cylinder and the piston must be of perfectly insulating because there should not be any exchange of heat between the system and surrounding. But in case of isothermal process, it should be perfectly conducting. And now this cylinder or the piston which is having area of cross section, let us consider it as A, and the pressure inside the cylinder be P, and V be the volume and T be the temperature of the gas which is enclosed in a cylinder. Now, when the gas is allowed to expand by moving the piston with a small distance dx, if we move a piston with small distance dx, the gas inside the cylinder will expand. Now, the work done is given by P into dV. We know how it is. Work done is equal to force into displacement, and force is nothing but, according to the expression of pressure, it is P into EA. Because we know that pressure is equal to force divided by area. So, F can be written as P into A. So, work done is equal to force into displacement. Our force will be PA and displacement is dx. Let us consider this as area and a small distance, that will consider it as length, and area into length will give us small volume, and hence it is P into dV. So, the work done is given by dW is equal to P into dV. The state equation for adiabatic process. As we know the equation of state for isothermal process, that is PV is equal to constant, we do have a equation of state for adiabatic process that is given by PV to the power gamma is equal to constant, and the gamma is nothing but the ratio of specific heats. So, from this expression we can write P as constant divided by V to the power gamma. So, we can now find the total work done. How to get the total work done? By integrating the above equation. So, what are the limits now to integrate? The limits are from initially the volume is V1, and now after expansion the volume will change, and hence the limits are V1 and V2. So, let us now derive the integral of dW, that is the small work done, is equal to integral of, in the place of P I am substituting constant divided by V to the power gamma into dV, and the limits are, as I said, it is V1 to V2, where V1 is the initial volume, V2 is the final volume. When you integrate the small work done, you will get total work done, and it is given by W, and constant can be taken outside, and we are writing integral of V1 to V2. This V power gamma, when it goes to numerator, it becomes V to the power minus gamma into dV. So, now V to the power minus gamma, it is of the form integral of x power n dx. So, x power n dx is nothing but x to the power n plus 1 divided by n plus 1. Now, we have integral of v to the power minus gamma into dv, v to the power minus gamma plus 1 divided by minus gamma plus 1. So, this minus gamma plus 1 can also be written as v to the power 1 minus gamma divided by 1 minus gamma, and hence we get constant divided by, this can be written as 1 minus gamma and can be taken out. divided by 1 minus gamma, and we are remaining with here in the numerator I have minus gamma plus 1, can be written as v to the power 1 minus gamma. Now after integration the limits are upper and lower limits, that is v1 and v2. Now according to the substitution procedure we have to substitute the upper limit in the variable inside the bracket minus the lower limit, and hence we will get w, where we are finding the total work done, and hence the letter is W here, not dW, where dW is the small work done. The total work done is W, which is equal to 1 divided by 1 minus gamma. Now as we all know, according to the equation of state for adiabatic process, PV to the power gamma is equal to constant. So in the place of constant now I can write PV to the power gamma, and when you take this to the inside the bracket by applying limits, we can write it as when V2, volume is V2, the pressure is P2, so I can write it as P2 V2 to the power gamma according to this equation into the variable here is V, so substituting the upper limit V2 to the power 1 minus gamma minus, now the constant will be PV according to the equation, but by substituting it is of the initial state, so hence it is P1 V1. So P1 V1 to the power gamma, then substituting the lower limit for this, I'll get V1 to the power 1 minus gamma. Now we can consider V2 to the power gamma and V2 to the power 1 minus gamma, and hence we can cancel out gamma terms, and we remain with P2 V2 to the power 1. And similarly here also gamma will get cancelled. We will get P2 V2 here and P1 V1 here. According to the equation of ideal gas, that is we know that PV is equal to mu RT. This is the ideal gas equation. Now PV equals mu RT, but we have here P2 V2. These are the variables of pressure and volume. After the expansion, then temperature can also be taken in terms of final temperature, initial temperature. So we can write it as W is equal to 1 divided by 1 minus gamma, when pressure is P2, volume is V2, temperature will be T2, and hence from this equation we can write mu R T2 minus mu R T1. Now here mu R is common, take it outside, and we will get the equation W is equal to mu R divided by 1 minus gamma T2 minus T1. This is the expression for work done in an adiabatic process. It is very important examination point of view. Let us now differentiate between the two processes what we have studied till now, that is the isothermal process and adiabatic process. We know isothermal process means, iso means same, thermal is the term which is related to temperature. In isothermal process temperature remains constant, whereas in adiabatic process the heat energy remains constant, is the basic difference as we all know. So in isothermal process, as we all know, temperature must remain constant. So to maintain constant temperature, the process must take place so slowly so that the system will get enough time for exchanging the temperature between system and surrounding to maintain constant temperature, and hence it is a slow process. Since adiabatic process, in adiabatic process we can observe constant heat energy, the system must not get enough time to exchange the heat energy with the surrounding, and hence it is a very quick process. So the process of adiabatic process is a fast process and isothermal process is a very slow process. Since there is no change in temperature, the name isothermal. But in case of adiabatic process, we can observe the change in temperature between the system and surroundings. And the next difference is there is exchange of heat between system and surroundings, but in adiabatic process heat remains constant and there will be no exchange of heat between system and surroundings. And in this case, system is nothing but the object which is under the consideration or under the observation. The part of universe which is under observation is called as system. And the walls of containers, say for example a cylinder or piston, they must be made up of a conducting material or they must be a conductor. But in case of adiabatic process, the walls of container should be made up of insulators so that no heat energy will get exchanged with the surroundings. And there is actual gain and loss of heat with surroundings. Since it is isothermal, the gain of heat or exchange of heat will takes place in isothermal process, but in adiabatic process we cannot observe that. So here Since the walls of container will also be made up of insulators, no actual gain or loss of heat with the surroundings. So these are the basic differences between isothermal and adiabatic process, and it is important for examination too. And next we have another type of process, that is reversible process. The name itself says reversible process, which means a process is said to be reversible if it is made to proceed in the reverse direction. Or what are the changes what we can see when the process is going on, when it gets reversible, all such changes will be retraced in the reverse direction. Example for this reversible process is a water cycle. And next is an irreversible process. So what is a irreversible process? Exact opposite to reversible. A process is said to be irreversible if it cannot made to occur in the reverse direction. So example, we can say that the rusting of iron or all the adiabatic processes are irreversible process. So next we have an important topic called Carnot engine. So what is this Carnot engine? What does it gives an idea about? Let us know about it now. So Carnot engine is nothing but an ideal heat engine which is free from friction and imperfections of actual engine, which means it's an ideal heat engine which is not affected by any friction or imperfection. So these are general parts of Carnot heat engine, which consists of a source which is maintained at temperature T1. The temperature's unit is Kelvin. What is a source? It is nothing but the hot reservoir where we can extract any amount of heat from the source. Next, it has got insulating stand. Insulating stand is used to place the working substances during the thermodynamic process. The next part is sink, which is also nothing but reservoir which has infinite thermal capacity and it is maintained with a temperature T2. And there is one another important part of Carnot engine, that is nothing but a cylinder which consists of working substance. So in Carnot cycle, we can place this working substance on source to extract the heat, to on sink to reject the heat to a reservoir, and also on insulating stand. And we will learn more about it in studying the Carnot cycle. As I explained, this engine consists of cylinder, heat source, heat sink and insulating stand. In cylinder, we can observe the working substance. A cylinder with a perfectly conducting base and perfectly non-conducting sides fitted with non-conducting frictionless piston containing an ideal gas as working substance. As I said, Carnot engine is also an ideal heat engine which is free from friction, and here the cylinder will be composed of or consisted with an ideal gas, and also a cylinder is fitted with a piston without friction or any imperfection. The cylinder will be having a conducting base to extract the heat and insulating side walls. So next we have source. What is a source? As I explained, it is nothing but a hot body of infinitely large thermal capacity. What do you mean by thermal capacity? The source which gives the temperature, the heat energy to the system. So thermal capacity maintained at a constant high temperature T1. The working substance draws any amount of heat from the source without changing its temperature T1. So the working substance, to do some work, it should have some energy so that it can draw any amount of temperature from the source. So next is a sink. It is nothing but a reservoir having infinitely large thermal capacity. It can also absorb any amount of heat that is rejected to it, and it is maintained with a temperature that is T2. So whenever heat is rejected, the temperature remains constant. Whenever the heat is rejected to the sink, the temperature remains constant, and it is nothing but the reservoir which can withhold infinite amount of thermal energy which is rejected to it. And next is insulating stand. It's a perfectly non-conducting stand used to place the working substance. So the PV diagram or the indicator diagram we must understand here. PV means pressure and volume. The diagram which is varying between the pressure and volume of working substance, or it is also called as an indicator diagram, which we are going to use in the study of Carnot cycle. So what is a PV diagram? A graph representing the variation of pressure with the variation of volume, and we will call it as PV diagram. So let us Now study the Carnot cycle by having an idea of Carnot heat engine and various parts of Carnot heat engine, what it is consisting of and what are the terminologies that we use, say for example pressure, volume, and the source which is maintained with temperature T1 and the sink which is maintained with temperature T2. So it's important, again, examination point of view, working of Carnot heat engine, or we'll also call it as Carnot cycle using PV diagram. What is PV diagram? It's variation of pressure with volume. So Carnot engine works in reversible cycle of 4 stages. So what are the 4 stages? One is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression as shown in the PV diagram. You can now observe here pressure is varying versus volume. Y axis along which the pressure will vary, and along x axis the volume. So here you can observe there is a reversible cyclic process. The PV diagram is explaining us about, let us say one by one in detail. So it undergoes in 4 processes, as I said: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So the first stage is isothermal expansion. So in this stage what happens? Initially the working substance of a cylinder, it is maintained with a pressure P1, volume V1, and the temperature of a gas inside the cylinder is at T1. So this gas, the ideal gas, will allow to expand isothermally by placing the working substance on the source. So when you place it on the source is maintained at temperature T1. So during this expansion, the gas absorbs heat and therefore it will get expanded. The pressure and volume of the gas will vary. How does it vary? As the gas gets heated, the pressure of the gas will decrease and volume will increase, and hence the curve is written in this shape. The pressure is decreasing and the volume is increasing during isothermal expansion. Initially the pressure was at P1, volume V1, and which is placed on a source with temperature T1. The gas will be allowed to expand and hence the pressure will decrease and the volume will increase. That is our first stage. It is mentioned by a curve AB. Say for example, if it is AB, isothermal expansion is represented by the curve AB. So next we will go to second stage. So what is the second stage? The second stage is adiabatic expansion. So in this stage the gas is allowed to expand adiabatically. So adiabatic expansion means temperature will also change, but there will be no change in heat energy. See, you can observe here since the pressure and volume only changing in the first process, the temperature remains constant in isothermal process. The pressure is P2, V2 after expansion, but the temperature remains same since it is isothermal, and hence it is T1 only. So in adiabatic expansion, even the temperature will change. So during this process, since it is adiabatic expansion, the pressure of the gas will decrease and the volume will increase. You can observe here the pressure is decreasing. The curve is like this. Pressure is decreasing and the volume is increasing. And since it is adiabatic, not an isothermal, pressure will also change. That is from P2 to P3, V2 to V3, and temperature is changing from T1 to T2. So in isothermal condition, only the temperature remains constant. In adiabatic condition, even the temperature will vary. So next is isothermal compression. You can see the third stage, it is isothermal compression. So this can be attained by placing the working substance on the sink. When it is placed on sink, the working substance will release the temperature to the sink, so that pressure and volume will change from P3 V3 to P4 V4, and since it is isothermal compression, the temperature remains constant and hence it is retained with T2 itself. And the fourth stage is nothing but adiabatic compression, in which the system will go back to its initial state since it is a reversible cyclic process. So this is the working of the Carnot heat engine, or the Carnot cycle we can say. It works in 4 stages: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. How do we get about all these variables? By having a knowledge of parts which containing the different parts of Carnot heat engine, that is the working substance. When it is placed on source, what happens? When it is placed on sink, what happens? And these are the mechanisms we can observe when it is placed at source, on sink and on insulating stand. So let us now write an expression for efficiency of Carnot engine on working in a Carnot cycle. So how do we get the expression for efficiency of Carnot engine? In Carnot heat engine, the working substance is nothing but ideal gas. So let us consider an ideal gas which is undergoing different processes. The first stage in the Carnot cycle is isothermal expansion, as we all know. Here we have considered 1 mole of gas and it is changing its state from P1 V1 T1 to P2 V2 T1, and we know that the work done in an isothermal process is given by W is equal to RT log of V2 divided by V1 that we have already derived. So let us write the same expression for work done in an isothermal process now for these variables, and our expression will be W1, that is nothing but work done in first stage, which is equal to R. What is the temperature here? Since it is isothermal, it is T1 log to the base E V2 divided by V1 according to the work done in isothermal process equation, and we'll call it as Q1 because when the working substance is placed on source, it absorbs the heat, and hence we'll call it as Q1. Let us take it as equation 1. So then third stage in the Carnot cycle, since we are talking about isothermal process here, to write the expression and to make it easy, we are considering first and third stage because they are isothermal condition. So third stage is isothermal compression of 1 mole of gas. Here you can observe the variables. What are the variables? P3 V3 T2 and P4 V4 T2. These are the variables of pressure, volume and temperature. Let us now write the work done in isothermal process expression according to these variables. Now the expression becomes W3. Since it is third stage, W3 is equal to R. T2 here you can observe T2 log E V3 divided by V4. We will consider this as Q2, which is our second equation. So now the efficiency of engine is given by eta is equal to 1 minus Q2 divided by Q1. Say for example, it is our equation 3. For the second stage is nothing but the adiabatic expansion. We know the state equation for adiabatic process is PV to the power gamma is equal to constant. This in terms of pressure and volume. But in case of temperature and volume also we can give the equation for state in case of adiabatic expansion, that is TV to the power gamma minus 1 is equal to constant, where T is temperature, V is volume. So in terms of temperature and volume, the equation of state in adiabatic process is TV to the power gamma minus 1. So let us now make use of this equation to derive the expression. For adiabatic expansion, look at the diagram. Adiabatic expansion, what is T? Our T is T1. So T1 V2 gamma minus 1, and here it is T2 V3. So our equation will be T2 V3 gamma minus 1, and we'll call it as equation 5. We have another adiabatic process, that is our fourth stage, adiabatic compression. Here the variables are P4 V4 T2, P1 V1 T1. Now writing the equation of state for fourth stage, we will get T1 V1 gamma minus 1 is equal to T2 V4 gamma minus 1. So this is according to the fourth stage. You can observe P4 V4 T2, P1 V1 T1, and hence here T1 V1 gamma minus 1 is equal to T2 V4 gamma minus 1. That's our equation 6. Now for simplification purpose, let us divide equation 5 and 6. That is 5 divided by 6 gives us, this is our fifth equation, this is our sixth equation, T1 V2 gamma minus 1 divided by T1 V1 gamma minus 1, which is equal to T2 V3 gamma minus 1 divided by T2 V4 gamma minus 1. Here I can cancel T1 and T1, T2 and T2, and we remain with V2 divided by V1 gamma minus 1 since the powers are same, which is equal to V3 by V4 gamma minus 1. Now these two are equal, so we can substitute the same in our previous equation, that is equation 4. So look at the equation 4 here, V3 divided by V4 we have, V2 divided by V1 we have. So these two are equal as we have proved. Now I'll replace this again by V2 divided by V1, and these two are same, we can cancel these two. Log E will also get cancelled, R will also get cancelled, and I remain with eta is equal to 1 minus T2 divided by T1. So that is what we have, eta is equal to 1 minus T2 divided by T1. In terms of heat, also we can represent this by eta is equal to 1 minus Q2 divided by Q1 is the expression for efficiency of Carnot heat engine. So in today's session, we have learnt about the expression for work done in adiabatic process, the differences between adiabatic and isothermal process, and also we came to know what is a reversible process or an irreversible process, and also about Carnot heat engine, Carnot cycle, and we have even derived the expression for efficiency of Carnot cycle. In our next session, I'll come up with some more interesting concepts. Until then, keep learning all of you. Thank you.